Hello, welcome to this discussion on frequency modulation. So this session is on frequency modulation, which is a second type of modulation that we are studying in communication electronics. The first being amplitude modulation, where we will be using the first parameter of a signal, that is the amplitude, to modulate the modulating signal onto it. So now we are going to use the frequency, that is the second parameter, and that will be modulated by the modulating signal. So let us see what is happening in the case of frequency modulation, as well as the mathematics behind frequency modulation. Alright, so let us consider a wave that is going to get modulated. So this is our modulating signal. For simplicity, we have taken the sine wave as the modulating signal. And this is our carrier, which is having a higher frequency. This one is an amplitude modulated signal, and you can see in the case of amplitude modulated signal, the frequency is not changing, but the amplitudes are changing. So the amplitude in each of these cases, as the time travels, it varies according with the input modulating signal. So that is the property of an amplitude modulated signal. But in the case of a frequency modulated signal, what we are going to get is a wave like this. So in this case, you can see this is the highest point in this wave, and this is the lowest amplitude point in this wave. So in corresponding to the highest amplitude point, you will be getting the waves densely packed together. But in the case of the lowest point, you will be having a more kind of a spread out kind of a wave here. So the difference between these 2 points is that here the frequency is higher, and this one, and at this point the frequency is much lower when compared with this one. Okay, so the frequency is the parameter that is getting more varied in this case, and the amplitude, you can see it is a constant throughout the waveform. Okay, so this is the case of a frequency modulated signal. Now let us see what is happening in the frequency modulation mathematically. So let us imagine a box that is a frequency modulator, and it has 2 inputs. One is the carrier input, the other one is the message that we are going to modulate upon. Those 2 frequencies are given inside the frequency modulation box, and you get the output as frequency modulated output. And when we analyze the frequency modulated output, and if we plot the frequency coming out of this output versus the time on y and x axis, then you will be getting a graph like this. And this is for the simple case of a sine wave. And you can see that this is frequency on y-axis, and the frequency is changing from fc to fc plus delta fc and fc minus delta fc. The frequency is changing. Okay. So in this case, we need to be familiar with 2 parameters. One is a center frequency, and the other one is a frequency deviation, delta fc. Okay. Let us see what those parameters are. So when you consider the carrier frequency, the frequency of this unmodulated carrier, that is defined by the term center frequency, fc. Okay, so that is the frequency when there is no modulating signal. Okay, and frequency deviation, delta fc, is the change in frequency that happens, the maximum change that happens from the lowest to the center frequency to the highest point, or to the center, or from the center frequency to the lowest point. So just take the difference between the frequency at this point in time and the frequency at this point in time. That gives you delta fc. Similarly, the difference between frequency at this point, that is the point at which highest amplitude is seen, and the frequency of the carrier frequency. Okay, so the difference between this and this will give you delta fc. Similarly, the difference between this and this will give you delta fc. So that is represented here. So you can see this, if this is your center frequency, then it increases up to fc plus delta fc, and it can decrease up to fc minus delta fc depending upon your input wave. Okay, the modulating wave. So at this point, it is at the fc plus delta fc. That is why the frequency is much higher here. And at this point, the frequency is much lower, and it is the lowest point that you can observe in your frequency modulated signal here. Okay, so this is having fc minus delta fc. That is the frequency at this point. Alright, so let us write the message signal like this. So your message signal is SM0, that is the amplitude, cos omega mt, and your carrier signal is SC0 cos omega ct. So let me ask you what the instantaneous frequency of your modulating signal is. So your instantaneous frequency that is the frequency at each point in time. So this is one instant, this is another instant. So there are a lot of instances happening all across the time scale here. Okay, so this is your time axis, and a single point can have a projection onto the time axis. The frequency at that point is called the instantaneous frequency. Okay, so let us see what is the frequency at each of the point, an equation for frequency. Okay, so I can write the instantaneous frequency as the center frequency plus a constant k times the message signal SM0 cos omega mt. So this is my instantaneous frequency. The frequency at each of these points can be represented by this equation. So you can see that there is a cosine variation in the instantaneous frequency. It is evident here. Okay, so that is here. So the message signal comes into the instantaneous frequency of the modulated output. So this is what is happening, and I can write this k times SM0 as delta fc. So this delta fc is represented as or k times SM0 is represented as delta fc. So that happens to be our frequency deviation. Okay, so this is the form of instantaneous frequency, and you can see that the FM signal output, that is this signal is having different kind of a frequency as each of the point. So you cannot use the simpler equation where SC0 cos theta is the angle of this signal. So you have an angle when it travels from this to this in time, you get your angle increased. So the angle is getting increased. So here it is 0 degree, it increases like this, and your angle theta is represented by omega into t. Okay, so this can be substituted with omega into t, but the problem is that our instantaneous frequency is changing. This omega is changing, it is not a constant in time. Okay, but in the other cases or here or you have the omega same. Okay, the frequency is not changing. In the case of carrier as well as in the case of modulating signal, the frequency is not changing, but in the case of FM, frequency modulation, the frequency is changing. So you need to have an integration coming into the equation. That is because at each instant the frequency is varying, right? If it was like this, the frequency was not varying, but when you modulate, the frequency is changing. Okay, so that means that you need to apply integration onto this. So it's not a constant, it is, you need to add up all the omegas. So it's not just omega I into t, it is omega I integral t omega I dt. Okay, so when I substitute that that for theta, then you get something like this. So theta is equal to integral omega I dt, which is equal to 2 pi integral fi dt. And what is fi? I can substitute that from here. So you have the equation for fi, that is in fc plus delta fc cos omega mt. So I will be substituting that into this, and I can split the integral at the plus sign, and you get two terms. The first term will be like this, and the second term will be like this. And what is 2 pi fc? That is omega c. And 2 pi delta fc, I can write it as delta omega c. Okay. And this theta, this is the equation 2 is representing theta. So I can substitute equation 2 in equation 1, that is the output of this modulator, that is FM signal output, that is SC0 cos theta. So instead of theta, I will be putting this equation. Okay. So when I put this equation, I get something like this, and I can call this factor delta omega c by omega m as the modulation index of frequency modulation, I will be representing it by M suffix F. Okay. But in the case of frequency modulation, modulation index should be much higher. Okay. So the ideal case is it is very high. So when you have modulation index greater than 1, it is good. But when the modulation index is much greater than 1, it is very good. So there should be some limit on to which you can apply this modulation index. You cannot increase it to infinity or so. Or it's not practical to have a lot of modulation, a very high modulation index value. So that will cause a lot of problem. The main problem is that when you analyze the spectrum given or allocated for FM broadcasting stations, it is around from 88 megahertz to say 100 and something megahertz. So this is a fixed kind of a frequency. You cannot shift or you cannot increase or decrease the frequency range allocated for frequency modulation, modulation broadcasting stations. So you have to allot all the other stations, broadcasting stations, into this small bandwidth. So there is a limitation in bandwidth. So whenever you are increasing your modulation index for the sake of good quality audio and all, then you are going to spend a lot of bandwidth for each of these channels. So there is a limit to up to which you can increase the modulation index for a frequency modulation, and for that limit itself the audio quality is very good, much good, much better than the amplitude modulation. So that is the advantage of using a frequency modulation over amplitude modulation. Alright, now when you compare AM and FM, it is like this. In the case of FM, the amplitude is a constant because we are modulating over the frequency. That is why the frequency is changing and the amplitude is a constant. But the reverse is the case of amplitude modulation. The modulation amplitude of the AM modulation changes, but the frequency is a constant. And in the case of frequency modulation, the modulation index should be much greater than 1. But in the case of amplitude modulation, it should be smaller than 1. And the range that is used for transmission is from 88 to 108 megahertz in the case of frequency modulation. But the frequency range for AM is from 540 to 1600 kilohertz. Similarly, the intermediate frequency that is used in the case of super heterodyne receivers made for FM is around 10.7 megahertz. But those made for AM is having an intermediate frequency that is 455 kilohertz. So these are the comparisons between FM and AM. And when you take the advantage of FM over AM, you can see that FM is having a very good advantage of having low noise perception. That is mainly because noise affects the amplitude of any signal rather than the frequency of the signal. That is why you have a very good reception without any noise. The second advantage is the operating range, and you have operating range much larger than the AM. That is because the frequency range is 88 to 108 megahertz, which is a much higher frequency range than 540 to 1600 kilohertz. And when the frequency increases, the energy of the wave also increases. That is why the range is much higher. And the third thing is high fidelity reception. That is, the audio quality of any frequency modulated signal can be increased by increasing the number of sidebands. And the number of sidebands is proportional to the modulation index that we are using. So if you increase the modulation index, then we will be having very good quality reception. The fourth one is a high transmission efficiency. When you compare the ratio of sideband power to total power, it is much better in the case of frequency modulation. That means more power is dedicated for transmitting the message signal rather than the carrier signal. But in the case of amplitude modulation, we have seen that even in the best case scenario, that is modulation index is equal to 1, then also we are only transmitting 1/3 of the total power in the message signal. Okay. So these are the aspects of frequency modulation, and we'll stop at this and go to another new session that is on pulse modulation in the next video. So thank you all.